If you crack open an atom, you will find protons and neutrons bound together by a violent, invisible tension, the strong nuclear force. Without this binding mechanism, every atomic nucleus in the universe would instantly disintegrate. This force requires a physical carrier. It is transmitted by elementary particles called gluons, massless messengers that bounce rapidly between quarks, locking matter into place. In 1972, physicist Murray Gell-Mann and his colleagues were mapping out quantum chromodynamics, the math that governs these interactions. Because gluons themselves carry the strong force, the math suggested they should attract and bind to other gluons. That calculation pointed to a bizarre physical anomaly, a theoretical particle made entirely of pure concentrated force, completely devoid of any mass-bearing matter. They called it the Glueball. For decades, physicists hunted for these bundles of pure force. The primary candidate they expected to find in their colliders was a specific theoretical particle known as the eta gluon. This is a model of the eta gluon based on early mathematical predictions. The physics demanded a stable sphere with a rigid mass requirement, landing somewhere between 1.5 and 1.7 giga-electron-volts. But when researchers ran complex lattice simulations and analyzed actual particle collider data, the pristine mathematical models fractured. The physical observations were chaotic and refused to align with the 1972 predictions. That gap between the chalkboard equations and the detector data forces a difficult question. Either our math for pure force particles is flawed, or nature is hiding a different mechanism entirely. To trace the source of this discrepancy, we have to look closely at the data captured inside physical detectors, specifically the Mark III at Stanford and the DM2 in France. Inside these machines, physicists never observe a pristine eta gluon. They only capture a brief, explosive event, a central energy node immediately shattering into microscopic fragments. This chart maps the exact composition of that subatomic debris. The shrapnel yields 50 to 60% pions, 20 to 30% kaons, and 10 to 20% eta mesons. A pure gluon state should decay symmetrically. This specific combination completely contradicts that expected signature. This wreckage is not random noise. By reverse engineering these remnants, we find that the original assumption about the particle was mathematically impossible. Zooming in on the chemical makeup of those specific fragments, the pions, kaons, and eta mesons, shows that they are composite particles constructed of only 2 or 4 quarks. Forging a stable subatomic particle pair requires exactly 6 quarks, yet our data shows detectors capture a maximum of 4. You cannot extract 6 quarks from a decay yielding 2 or 4. The physical remnants prove the original entity lacked the components to achieve stability. Those missing quarks are the mathematical footprint of an energetic shortfall. The structure we labeled a glue ball was doomed before it even fully formed. In May 2026, researcher Nathaniel Faxon Cherier published a thesis arguing that decades of particle physics have mischaracterized this entire phenomenon. Cherier strips away the pure force assumption, stating directly that the eta gluon and similar observed events contain 0 pure gluon states. Instead, Cherier redefines the glue ball as a failed subatomic particle pair. The strong force attempted to cross the necessary energy threshold to forge mass, but the system simply ran out of energy mid-process, collapsing before a stable geometry could materialize. The glue ball operates as a cosmic misfire, a fossilized record of the strong force attempting and failing to create physical matter. Accepting this failure requires a reevaluation of strong force dynamics and the baseline models of quantum chromodynamics. This phase transition diagram maps out the glue ball's actual domain. It sits directly on the boundary line, trapped forever between invisible force interactions and the exact threshold where tangible mass is forged. The most valuable insights in physics lie in studying these energetic misfires. They map the exact threshold where our physical universe struggles into existence. To explore more of the universe's greatest boundaries, return to MDU, and be sure to like and subscribe.